Swayam Prabha. Digital India. Educated India.
Okay guys, so in the last class we have been discussing the mean square displacement relations for another chain model which we called as the worm like chain or the Kratky Porod model. And the description went something like this. So, we have a polymer chain. I define a contour variable S that goes from 0 to LC, where LC is my contour length. I am interested in finding the end to end displacement vector RE. RE I can write in terms of the position vector R, which is now a function of x s along the contour. So, this is equal to R LC minus R of 0, and what we said is if I take a limit b going to 0, I can talk of segment vectors or bond vectors as the tangent to this particular graph, and based on that what we derived was the mean square end to end distance was 2 LP square LC by LP minus 1 plus e to the power minus LC by LP, where LP is what we refer as the persistence length that characterizes the stiffness of the polymer chain. So, now what we will do, we will take two extremes, one in which the persistence length LP is very high and another case when this LP is very small. Okay. So, just to recall briefly, the correlation of the tangent vector went like exponential of minus s prime by LP. So, in that sense the magnitude of LP characterizes the amount of correlation that we have in the system. So, let us take a limit when we have LP that is much higher than LC. That means my persistence length is much higher than the contour length, and in that case what we can do is we can of course see that in this case my LC by LP become very small. So, I can do a Taylor expansion of the exponential term here because the argument of exponential is a very small number, and what do we get is exponential of minus LC by LP as something like 1 minus LC by LP plus LC square by 2 LP square minus LC cube by 6 LP cube, just using the formula that for small x e to the power minus x goes like 1 minus x plus x square by 2 minus x cube by 3 factorial or 6 and so on. Okay. So, if I now put this expression in the previous expression, what do I get is my RE square goes like 2 LP square LC by LP. This is an approximation minus 1 plus 1 minus LC by LP plus LC square by 2 LP square minus LC cube by 6 LP cube. So, there are of course cancellations, and what we end up getting is something like LC square multiplied by 1 minus LC by 3 LP and so on. Okay. And now you can see if my LC by LP is really very small, that is when say persistent length is almost like infinity, what do we have is in the limit LP is going to infinity, then this term, the second term also drops down, and what do I get is my RE square goes like LC square, and what it essentially means is my end to end distance become equal to the contour length, and what it means is the chain is actually like a rod, because only in that case the contour length will be same as the end to end distance. Okay. This is what we refer as the rod like limit, and that is obtained when LP is much higher than LC. Okay. Now, look at the opposite extreme when the LP is very small, and let us see like what happens in that case. So, again we will reproduce the formula here. So, the mean square end to end distance is 2 multiplied by LP square LC by LP minus 1 plus e to the power minus LC by LP. And now let us say I look at the extreme. So, earlier case we looked at when LP is much higher than LC. Now, we look at when LP is much lesser than LC. Okay. So, that means LC by LP is much higher than 1. So, in this case you can see I can really drop the exponential term, because the power to the exponential is a negative number and that is very small, very high. So, this will drop, and what we will have is RE square is approximately equal to 2 LP square multiplied by LC by LP minus 1. Now, since LC by LP is much higher than 1, we can also drop this particular term, and then we have 2 LP LC. Okay. Now, try to recall the relationship that we derived for a flexible chain. What we had was RE square is equal to NB square for the models we derived for flexible chain, and look at like what the LC will be equal to. So, of course, provided that we use many segments to represent the polymer chain, actually in the limit when B goes to 0, what essentially we have is LC will be equal to N multiplied by B, that is the number of segments multiplied by B. That will be true when the B value is taken to be very small. Okay. So, if I compare now this expression with that expression, you can see that LC is analogous to my NB there. So, this term must be analogous to my B, and for that reason we say B is equal to 2 LP or LP is equal to 1 by 2 B, which is something that we discussed earlier that the persistent length must be equal to half of the Kuhn length. Okay. So, in this particular limit we can say the chain is flexible. Okay, and now we have already discussed a couple of cases where the chain has to be stiff. The first case we said was if we have a delocalization of valence electrons, in that case chain is stiff. If we have a bulky side group, in that case a chain is stiff. If we have a strong polyelectrolyte where there is Coulomb repulsion between the segments of chain and the Coulomb repulsion is very strong, in that case we have stiff things. If we have, for example, hydrogen bonding between segments like the case of a DNA molecule, in that case the chain is stiff. But even otherwise, even if I look at a particular polymer chemistry and if I look at say small chains containing lesser number of carbons, they have to be more stiff compared to the chain containing more number of carbon, for the simple reason that I will require more segments to represent the chain, or the number of conformations will increase if I increase the number of carbons. Actually, in the lectures in the beginning, I said the number of conformations roughly goes like 3 to the power m, where m is the number of repeat units. So, using that idea, what you can think of is smaller chains containing fewer carbons or oligomers will be always more stiff compared to larger chains or the actual polymers. Okay. So, in most systems for the same polymer chemistry, if I change the number of repeat units and I look at my Re square, what you will get is in the very beginning my Re square will go like n square. Okay. So, let me draw it slightly nicely, just because I just said that the mean square displacement is mean square end to end distance is going like Lc square, and Lc is increasing as n is increasing. So, my Re square will go like n square, but after that we recover the behavior Re square going to n for longer chains. Okay. And this has been observed in many polymer chemistries, that for smaller values of n we do see a rod like behavior, and then it transitions to a flexible behavior for longer chains. And the Kratky Porod model is very helpful to look at how the transition takes place from that regime to this regime. The models we derived earlier are only applicable to this regime. We can assume the chain to be rod like somewhere here. For the intermediate regions, when the chain is between the rod like and flexible regime, the Kratky Porod model become particularly useful. Okay. So, I want to now hint at like some ways of looking at the end to end distance in actual experiment or in a simulation. So, in an experiment, of course, you do some kind of an scattering and get the mean size of a chain, and from there you want to calculate the end to end distance. Actually, what turns out and what we will show in the next week lectures, that the quantity to measure is not the end to end distance, but what is known as a radius of gyration. That is one way of doing it. The other way of doing it is I try to do some kind of a simulation that incorporates the detailed chemistry into it. Okay. And one thing that is becoming more used in the polymer literature is what is known as atomistic simulations. Where I can really represent the polymer chain not by a toy model, but by the complete chemistry that we can incorporate. That means I will represent the polymer chain as composed of all its atoms. So, for example, this is my polyethylene molecule. The limitation though is all these simulations will not really work if the number of carbons become very high, just because the system size become huge. Think of it like I am not only looking at the polymer chain in isolation, the polymer chain must be in a solvent, and in that case we also need to model the solvents which are present around it, and it turns out that by the current computational resources I can only model like chains of say 20 or 30 or 50 carbons, not beyond it. Okay. So, in the regime where the chain is rod like or going towards flexible behavior. So, in this particular regime, when RE square is going like n square, in that particular regime I can also do atomistic simulations, but it will not go like very high until there. Okay. If I work with like TWI models, then in that case I am right here. Which are the TWI models for the random walk, and if I am doing like a Kratky Porod, then I am capturing this entire regime, but that still remains to be a TWI model, right. So, what we can do is we can validate or find out some of the parameters of Kratky Porod model also by using the simulations, if we are able to get this particular crossover where the chain goes from a rod like regime to a flexible regime, and this remains, I would say, a challenge in the polymer simulations, but it is now possible for certain polymer chemistries. Okay. The other point here is apart from the polymer chemistry, what also is important is the environment of the polymer chain. So, a polymer chain can have different mean square end to end distance if I put the same chain in different solvents. So, the amount of stretching, the amount of stretching or the amount of swelling of a polymer chain would depend on what solvent it is present in, whether it is favorable to the polymer, whether the polymer dissolves in that solvent, whether the polymer likes that solvent and so on, or whether the polymer hates that solvent, and that is like one factor that one has to consider. The other factor is the effect of temperature. So, the same polymer chain can show different behavior at different temperatures. So, it can be, for example, more stretched at a certain temperature, and if I go to, for example, a higher temperature, it can become collapsed, or vice versa, it can be stretched at a lower temperature at a higher temperature and becomes collapsed at a lower temperature, and so on. Okay. So, these effects are some things that we have not so far considered in the TWI model, and for this reason we are limited to the scaling behaviors that are either in the ideal chain limit or in the rod like limit, and later on in the class I will tell you when does we deviate from this particular scaling laws and how to address that in the models that we have discussed. Okay. So, the other thing I want to remind you is, so far we only looked at the short range correlations along the contour, but there can also be like long range correlations. For example, these 2 points are very far if I look at their distance along the contour, but they are physically very close. Okay. And there is something called an excluded volume interaction that comes into play when 2 segments of polymer chain, irrespective of their distance along the contour, come together. And it turns out that these interactions depend on the solvent and the temperature, and if I try to include them into the model, I will have deviations from the ideal chain behavior. This has been observed experimentally as well for many polymer cases, and we will discuss that in the coming lectures. So, with that I stop here. Thank you.